So it's a pleasure to have today's speaker, the Professor Arindam Ghosh from ISC Bangalore, and he's quite well known in nanoscience in India. So he didn't need much introduction, but just to carry forward our colloquium tradition and for the sake of our student, I would like to add few words about him. That he completed his MS and PhD from ISC Bangalore in 2000, and then subsequently he went for postdoc in Cavendish laboratory in Cambridge University, and he stayed there until 2005. And in that same year, he joined ISC Bangalore as an assistant professor. So since then, he has been contributing a lot in nanoscience in India. His research interest mainly lies in the structural, electronic, and magnetic behavior of nanomaterials, and he works in many fields that you can get by going through his website. He has several patents from his lab in ISC, and at present he is also associated with Nanoscience and Nanoengineering Department of the ISC Bangalore, Center of ISC Bangalore. And there are many awards that he has received due to his quite active contributions since couple of decades in nanoscience, and few of them like Swarn Jayanti Fellowship in 2009, 2012 he got Santi Swarup Bhatnagar Award, 2015 he got Young Scientist of India. He is also a fellow of Indian Academy of Science and National Academy of Science. And since last couple of years, he is quite actively working on 2D nanomaterials, especially twisted bilayer graphene. And today he'll be saying much about that how the engineering can play a very important role in bringing some beautiful effect out of these two-dimensional bilayers. So with this, I would like to invite him for today's colloquium on engineering the flow of charge, light, and heat with atomic layers. And I hand over the forum to the Professor Arindam Ghosh. And before that, I would also like to thank Saurabh Basu for coming with this idea to invite, let's invite Arindam, although he will be quite busy, but let's try and get him on the board just for sake of our students. And he also shared many interesting stories since his undergraduate days with him. So just before starting, I would like Saurabh Basu to say a few interesting thing about Arindam.
Oh, thank you. I mean, you don't have to thank me, Pankaj. So just for the audience, he's an excellent cricket player. So much so that he played first class in Bengal, first class cricket in Bengal when he was in his college, and then went on to play county cricket when he was in Cambridge. So, and in his own words, he has done more cricket than postdoc, which of course we don't believe, but I believe that he has done both and equally well. So over to you, Arindam, and thanks for joining us. Thank you.
Oh, you're welcome. Okay, I mean, let me just first, all right, I hope you can see, just let me know if you can see it, right? Pankaj?
Yes, we can see it, slide. Yes.
Yeah.
Good. Okay, good. First, thanks, Pankaj, for the introduction, Saurabh, for letting the secrets out. Yeah, I mean, we used to do both, both during my PhD days at ISC and outside, and even as a faculty. So it's always very nice. Okay, good. First of all, it's a pleasure to talk to IIT Guwahati crowd again. I have been getting there off and on, but it's always good to spend time. And hopefully in the near future, when all these virus thing goes away, we should be meeting again. I'm going to talk a little bit about what we have been doing in light matter interaction and how to engineer new devices with atomic layers. I'm sure many of these are known to you because these are very in field of research. So let's get ahead with it. I mean, I'm quite sure graphite is something which is not unknown to anybody. I was told that, you know, I would like to start with a little basic level, but then we will graduate to more cutting edge research. So hopefully there is a take-home message for everybody out there. Okay. So graphene has, you know, created a lot of interesting possibilities. And we now have device paradigms that's coming up, because from now the European Union is extremely excited in application of graphene, from flexible electronics, papers, and to strain engineered materials and so on and so forth. What is the number of papers since this is slightly older statistics now is thousands, tens of thousands per year on graphene alone. Now from there are about more than 200 companies on this topic that they're all over the world. So you can imagine how heavily this field has developed over the last decade and a half or so, 2004 to up to 2020 today. It's expected about 0.5 billion market just on graphene in the next 2 or 3 years, or maybe 4. So yeah, I mean, all these things really started when we recognized, or this was recognized much earlier, that graphene belongs to this class of compounds, which is called layered solids, where the layers are strongly bound in plane, but they are not so strongly bound out of plane. For example, you can see the van der Waals force between two layers in graphene is about 100 to 1,000 times less than a standard three-dimensional covalent bonding or ionic bonding. Okay. So that made the whole field start when you could exfoliate those materials, and it's huge. Now the family of these materials is, in principle, what can be exfoliated, and look at the numbers here. So if you have typical binding energy between two layers, approximately in the order of 10 to 20 milli-electron volt per square angstrom, it's easy to exfoliate. That means you take two tapes and you just cleave the material and it will form nice layers, okay? Nice, along a lattice plane, you can exfoliate them. There could be about 1825 according to calculations now. So imagine the phase space, of which we know probably about 30 to 35 can be separated in terms of exfoliation and stabilized and made devices of today. And this number is increasing. Okay, and these numbers are staggering, because even with one, like graphene, the number of properties we can get is massive. And I'm going to show you a little bit of that. Okay, so this whole concept of exfoliation is the reason why we could get this system of these layers on a substrate. Okay, usually these substrates are silicon oxide substrates, and once those substrates are created and you use a scotch tape to stabilize, and this is a very well-known technique now, one can actually make devices by putting contacts, okay, electrical contacts. And this is how a typical device look like. Now, once you have a device like that, you can make a field effect transistor. So original graphene paper actually was demonstration of a field effect device, in which you use the heavily doped silicon and apply potential voltage on that, in which the silicon dioxide layer acts as a dielectric. So the graphene layer on top acts as is capacitively coupled to the gate, and you can change the electron density or the hole density. So if you make the gate voltage positive, you induce electrons, and if you make the gate voltage negative, you induce holes. And in both cases, the electron or the hole density, the charge density goes up and the resistance comes down. So that's the field effect device that one is talking about. Excuse me. Now let us go a little bit more detail about the band structure of graphene, and this is why I wanted to say that, you know, the 1825 materials that are potentially possible, even graphene alone, one, is exceptionally interesting from a number of point of view, and I'm going to show you that. Okay, so this is hopefully some people who are trying to understand what they would like to do in this field, hopefully you will get some ideas. So, so for example, if you have a band structure of graphene, which essentially means that, which is a hexagonal crystal lattice, and if you take the Brillouin zone, which is also hexagonal, and you will simply take a tight binding model, and you will be able to solve that to get a band structure that you can see over here. Let me just try to see if I can. Yeah, okay. So you can see that these, I don't know whether you can see my cursor, but anyway, hopefully you can. So if you see these points where the conduction band and valence band touch, they are what you call the Dirac points. And around the Dirac point, you have this conical band structure, which is why the dispersion relation at low energies is linear, and graphene is electrons behave as light, although at much lower velocity, which is about 10 to the power of 6 centimeters meter per second, you get a linear dispersion. Okay, right. So that's the case of infinite graphene, and this is where the interesting thing starts. What about the semi-infinite graphene? And the semi-infinite graphene means that you will have two edges. So this is a square. So you have, if you see this edge, which is on the left. By the way, can someone tell me whether they can see my cursor, or I have to do?
Yeah, we can see your cursor.
Okay, good. So if you see this, my cursor, this is called a zigzag edge, and when you see this bottom one, it's called a armchair edge. Okay, because of the topology of the carbon atoms. Again, if you simply do a standard tight binding theory, tight binding model calculation, it's very easy. We just have to take the densities from each or every atoms and then just simply add it up with appropriate boundary condition and the condition of orthogonality. Okay, then you will see something really interesting about these two edges behave very differently. So, for example, if you have an armchair edge, you will get a gap structure, which is at 0K, there is a gap. Whereas if you have armchair edge, this is zigzag edge. In the zigzag edge, you get a completely different behavior, which is there's a zero energy state. Okay? So there is one particular band which essentially goes becomes zero energy, and this is something which very similar to what happens in topological systems. But this is not topologically protected, because if you create lattice defects, then these zero energy states go away. Now, we were one of the first set of people to actually show that zero energy states could be could host dissipationless current even at very high temperatures, at room temperature. So you can see the conductance of these zero energy states can actually be E squared by h, which essentially is the quantum of conductance, which is like a one-dimensional conductance state, and this quantization was observed at room temperature. So this is where you can use graphene edges for making circuits, which can do.
Arindam, just
sure.
Is there armchair? There's no restriction on the number of unit cells for it not to have a zero mode.
The zigzag, you mean to say, the armchair will never have zero mode. The zigzag will have zero mode, but
the armchair also depending on certain length, wouldn't have also it have a zero mode?
No, as far as I know, by finite length of the armchair.
Finite length. I think there's some restriction on the length, which is some 4n plus 1 into some a by 2.
Right. So we have taken very large m here. Okay. So at a very large m limit, you don't get a zero mode. And so this is something which you need to check. As far as I understand, this is done on 96n or something of that sort.
Okay.
Excuse me. But in the case of zigzag mode, even if you have got a very large n, but you have got width to be small, then these zero energy states go away. So you can open a gap at zigzag as well by finite width of the ribbons. Okay. Yeah. So anyway, so we have been working. I don't want to talk about too much on this because today's agenda is different. Okay. Then bilayer graphene is very interesting as well, because here you have got 4 electrons in a single unit cell, 2 from each layer, and that leads to, in the low energy band, spinner type with layer 1 and layer 2 acts as the spinner, okay, like an equivalent spin. Okay, so this is because of the interaction between the layers. You don't have the linear band structure anymore, but you have parabolic band structure, but with a spinner. And that leads to something very interesting, to marginal topological insulator properties. I'll just give you a very brief look how it looks. For example, this have this, you take two layers of graphene, but they are decoupled from each other. Each has a conical band structure, but then you apply an electric field on it, say for example, and then you shift them because you create a voltage difference between the two. And then you turn the interaction on, suppose, okay? So if you turn the interaction on, then you see you can create these hybridization, and then you gap out, okay? Not just you gap out the bilayer graphene, but also you can see at the bottom, a part of conduction band goes into the valence band, and part of the valence band goes into the conduction band, which is what you call a phenomenon of band inversion, which is why bilayer graphene is expected to be some form of a marginal topological insulator. Again, there is no spin in it, but that's simply because there is a spinner kind of a geometry coming from the two layers. Yeah. And we had done that recently. We showed that indeed there are two other groups also which have done this. We showed that when you gap out bilayer graphene, you actually see the current primarily along the edges, and that was shown through some noise measurements, which I will not go into. But these are very interesting aspects of graphene alone. Molybdenum disulfide, for those who know or working on, are very interesting material. They are semiconductors in some sense of boring semiconductor because they're parabolic band structure, but they have very interesting properties. They can be extremely narrow and small. In thin monolayer of molybdenum disulfide can give rise to very large current. The conductance change like a field effect transistor. Exactly. It is different from graphene in the sense that you can change the conductance by several orders of magnitude by changing the gate voltage below in the substrate. Okay. But by the way, please feel free to ask. I don't have to finish everything I have to say, so I will just stop at the end when time is up.
Since you said that, is this band inversion very similar to the mercury telluride and cadmium telluride heterostructure with
No, it's not. So that's a very interesting question. Answer is no. So there it is strong spin orbit interaction, which leads to the band inversion, right? And that protects the topologically the states against any form of spin scattering. Okay, but standard disorder will be essentially the will be bypassed. So those states are protected against charge disorder, but if you put in spin impurities, the protection is gone. So there the protection is by spin orbit interaction. Here the protection is layer valley interaction of some form. Okay?
But so is it so you have a Bernovich, Hughes and Zhang kind of Hamiltonian? We can write it.
No, not fully, unfortunately. This is so that's why it's called a marginal topological insulator. The Chern number is different. Okay, in this case, and it's I think 2 here, and one has to check it out exactly how much. So it's the topological protection is not the same as the that 8GZ model or whatever it is.
Yeah.
Okay. So there's a fundamental difference between bilayer graphene and that, and those which are protected by spin orbit interaction. Okay. So, but in case of molybdenum disulfide, we have not just very interesting field effect transistor property, but they also have got very interesting structural polymorphism, in which if you have the standard naturally occurring semiconductors of 2H type, okay. But what happens in the case of if I essentially shift one of the layers of the top by one layer, which is called heterostructure, this becomes a metal. From a semiconductor, this is naturally occurring semiconductor 2H structure, and then it becomes a metal. But if it turns out that this 1T metallic structure is not really a stable structure, but lattice distorts because of some soft phonon modes, and it becomes what you call a 1T prime, or the disordered octahedral structure, and that turns out to be a spin Hall insulator. But here, of course, strong spin orbit interaction is the protection mechanism, and people have calculations are now available, and there are experiments available as well, primarily through scanning probe, in which you can see that in case of an octahedral molybdenum disulfide, you see the band inversion happening here. Okay? I'm not going to go into detail at this stage. What is the topic of material today is, of course, using these molybdenum disulfide and use its extremely high sensitivity to light. So that's another aspect of these chalcogenide, transition metal dichalcogenides, in which they have a very strong density of states near the visible range at the edge of the conduction band, and that allows extremely large scattering cross-section of light by this material. As a result, even a single atomic layer or molecular layer can absorb 6 to 10% of light, which is impossible for usual bulk materials like silicon and so on and so forth. Okay? So as a result, you can see this, if you shine light, there is a huge response in current, and that has been used as a for various purposes. And because of you can get large number of these materials over a very broad bandwidth, you can cover a very large, nearly 15 orders of magnitude or 12 orders of magnitude of frequency, in which you can sensitize these materials. Okay, so this is why there is a lot of interest in light matter interaction with this material. Okay, if that is not enough, what we have been working on is what you call the van der Waals Lego, in which you put one material on top of each other. For those who haven't seen this video, essentially what you do is you take these layers and put it on top of each other in a sequence that you wish to. This is, of course, done, this technology now, there are several groups in the world which has now, but we were one of the earlier ones starting this process in 2013, nearly about 7 years ago. But what's interesting about this is that you can make a huge different combinations, very large number of combinations, based on what you would like to do, or the functionality or the physics that you would like to see. Okay, so I'm going to give you some examples on that. For example, if you want to simply make a high quality electronic device, you can see that you can just put graphene layer in between two boron nitride layers. A boron nitride essentially is a perfect lattice matched partner of graphene. As a result, if you put graphene between two boron nitride layers, it sees no disorder, and hence its electrical mobility becomes very large. You can see by putting a standard on silicon oxide, graphene is just about 5,000 to 10,000 mobility. But if you encapsulate it with boron nitride, the mobility can go up to 100,000. These days, it can go to 1 million, and so on and so forth. Okay, so that's one of the immediate advantage, but that's material quality. But you can actually do a lot of interesting stuff as well. So my group essentially does use various kinds of aspects of this layer engineering of van der Waals heterostructures. I told you already about our boundary states of graphene, what we try to do. In addition, we have strongly involved in light matter interaction, thermoelectricity, and I'm going to talk about those two on the top in a combined form. In addition, we actually these days are very excited by the neuromorphic designs in which we can make memory devices. Tathagata Paul has just finished his PhD on this, and these 2D layers, if we appropriately stack them, they can become a very different type of memory which can mimic the function of the brain. Okay, so but again, I'm not going to talk about that today. All right, so let us try to understand about the charge transfer and what's the physics that's on there. There are a lot of people who have contributed to this. Unfortunately, I could not put, as you can see, I'm running out of space, so I have to do something else. Past members who are present now. There's a strong collaboration with a lot of people, our faculty colleagues of mine here, with different material aspects. I mostly put people who have contributed to publications so far, but there are a lot of people who are working on this. Please excuse me if you don't find your picture here. Okay, so why this is so interesting in terms of charge transfer across van der Waals layer. It's interesting because it gives you a very a new handle or a new tuning, a new knob, in which you can combine the physics and device aspects of a completely different material, chemical origin, of different materials of different chemical origin. For example, because they're so close, in spite of the gap, which is the van der Waals gap, which is about 0.3 or 0.4 nanometer, you can transfer electrons very, very quickly from one layer to the other. And this is something which has been shown now. You can see the transfer can happen within 5 picoseconds or something of that sort. And this naturally raises possibilities of a new kind of detectors. I'm going to show you that, or many other interesting physics. One of the key questions here is that what is the role of momentum conservation or energy conservation when a charge goes from one layer to the other, because it is changing its symmetry, right? So there are a lot of fundamental questions, as well as there are a lot of application-oriented questions. So I'll tell you one by one. So this whole thing started many years ago. As I said, we could make graphene TMDC, or the TMDC is transition metal dichalcogenides, which has got either molybdenum disulfide or tungsten diselenide structures. Okay. In which what happens, if you can see very carefully here, I'll spend a minute here. So you have got graphene on top, and then you have got the TMDC layer. The graphene, if I apply a gate voltage at the bottom, exactly the way other things happen. The TMDC layer is far more insulating, so it doesn't really do much. So you can see the graphene's standard characteristics, in which the resistance goes down around the Dirac point expected. But when you are at these 2 points, either electron doped on this side and hole doped on this side, and you shine light on it, then you see a very interesting behavior. You see the resistance of the graphene layer, I'm measuring resistance of graphene, changes when you shine light on it. Okay? When you are electron doped, which is here, the resistance decreases, means that the number of electrons has gone up. Whereas when you are on the hole side, then the shining light make the resistance go up. That means the effective number of carriers has gone down. From this, it becomes clear that when you shine light, some electrons from the layer underneath has been transferred from TMDC layer to the graphene layer. So this is what you call a photoresponse. Okay. Now, if I convert the resistance change into change in current and then normalize it, this is the normalization by the power of the LED that we are using to illuminate. There is this photocurrent, and the relationship is called a photoresponsivity, gamma. And that number becomes 10 to the power of 10, or something of that sort. And this is an astronomically large number compared to the intrinsic photoresponsivity of most material, and that is in the order of 1. So this was some form of a paradigm shift in optoelectronics per se when we came up with this in this hybrid model. Okay. As a result, you can see that today it is nearly 9 to 10 orders of magnitude more sensitive than most of the existing optoelectronic element that is available to us. Okay, but what's the physics? Let's go to the physics. So the physics essentially is what you call a photo charge transfer and photo gating. That means when the electron essentially goes from the layer bottom to the upper layer, it essentially goes into the sink because it is kept at zero potential, but the hole which is left behind is acting as an additional gating agent. So it gates like positively the graphene underneath. Okay. As a result, you see the gate effect is maximum where the R versus VG, the transfer character is the steepest at this point and at this point. That is where the change in resistance is maximum. And the change in resistance due to shining of light is proportional to the derivative of the resistance with respect to gate voltage. So this is what we call a photo gating effect. Okay. It turns out that it's very easy to understand that this is entirely because of exciton formation in the molybdenum disulfide layer. You can see that when light falls, you create an exciton in the TMDC layer, and then exciton splits immediately. And you can see that photocurrent is finite. This is the photocurrent, the black one, is finite only when there is the exciton peaks, only when the energy of the photon is higher than the excitons of the TMDC layer that we are using. Okay, so essentially breaking of the exciton is the reason or the physics of this photodetection. However, the question is then, how does an exciton dissociate into free free carriers. So it turns out that this is not very difficult. The moment light comes in, the electron and holes are created. This is how the energy band diagram look like. You can see the graphene is about work function of 4.56 electron volt, and that of molybdenum disulfide or most of the chalcogenides is in the orders of 4.3 electron volt of electron affinity, and that leads to these kind of alignment. Okay, and when light comes, electron forms below a certain amount of energy called the binding energy below the conduction band. That's the excitonic level. It sees a lower energy state which is available to it, which is graphene, and immediately it ultra-fast adiabatic charge transfer takes place. How does that charge transfer initiates is a question that is still a matter of debate. There are people who actually came up with the effective Hamiltonian, which initiates the charge transfer from the MOS2 layer or the chalcogen layer to graphene. Okay? But it is an ultra-fast charge transfer. But if it is ultra-fast charge transfer, it is not so. Experimentally, you can see that normally this ultra-fast charge transfer happens in the orders of 10 power of a picosecond or less, whereas we see that change in resistance is actually very slow. You can see when light is switched on, the resistance changes over really tens and hundreds of seconds rather than 10 to the power minus 12 seconds, right? So the question is what is happening, and this change also depends on the power of light that you shine on it. So it turns out that Tanveer Ahmed, who just finished PhD and for postdoc, solved this problem, and he said that look, there could be a back and forth. It's not just going from one side to the other, but there is also a return of electrons from the graphene layer back into the excitonic states in the chalcogen layer. This is very similar to what happened in the back transfer of charge even in solar cells, organic solar cells. And you can form a rate equation like this, in which this effective time of charge transfer is really given by a balance of the charge transfer rate from tau TR is its rate from chalcogen to graphene, and tau return is the recovery. This is tau R, which is the recovery time of the exciton within the chalcogen layer. So if you put these things together, you get a simple first order differential equation after some approximation, which gives you an exponential relaxation. Okay, and that gives us a very correct order of magnitude of the expected time scale as well. Given the fact that the number of photons you apply is proportional to the power of excitation, it also shows that when the power is very low, then this time will become very large, as we see experimentally as well. Okay. Using this, actually, Tanveer could actually measure the binding energies as well. So this is the physics of charge transfer. Okay. So this field has gone quite a bit after that, and I'll just say that after we came, after the publications of graphene MOS2, then people have been making LEDs, people are making solar cells, tunnel diodes, and so on and so forth. Okay, so there have been a lot of interest going on in this area. We ourselves have pushed it quite a bit. For example, we wanted to ask the question: okay, if this is so sensitive, can we make single photon detection? And I'm going to show you a bit on that. And in addition to that, there are a lot of other directions that we are working on. For example, we're trying to understand whether instead of charge, we can maximize the energy transfer from chalcogen layer to the graphene layer, because that would be really a fast process. Okay, just to give you how we can make it even lower noise photodetection, you need to understand what is the signal to noise ratio in a photodetector like this. It's essentially given by two types of noise. The denominator needs to be as small as possible. This is what you call F is called a gain noise, in which this is an optical gain that you have when you shine light, and the other is noise in electronics. Usually these two degrade the performance of a photodetector. Normally in the case of a graphene MOS2 photodetector, unlike standard single photon counters, this X's gain noise is 1. F is 1, or the gain noise is 0, simply because the flow of current is physically separate from where the absorption of light takes place. Absorption of light takes place in molybdenum disulfide, and the current flows through graphene, so which is why F is actually just 1. So we are usually dominated by the noise in electronics, and which is determined by the dark current. Okay, and if we can operate this at a very low dark current, we will be able to measure even single photons, and that's what's the plan. And we made a device like this with bilayer graphene, because in bilayer graphene you can apply an electric field from the top, and you can open the band gap, yeah, like the way I showed you in the beginning. So if the band gap opens up, then the dark current goes down, and we will be able to make extremely low noise photodetector. And this is indeed what Kollol and others, Tanveer and others did. You can see every pulse of light, there is a change in current in this heterostructure, where graphene acts as a top gate and a window through which light comes and hits the molybdenum disulfide layer underneath here. Then the electron goes into the bilayer graphene, and you get the photoresponse. Okay. As a result, what happens is we get these photoresponse, and we take statistics of a large number of pulses, and you can see you can get the single photon Poissonian distribution. So even when the bunches have single photons, you have very strong response in the system. So it was quite interesting to see a demonstration of single shot detection of single photons in 2D material structures. There are many other questions. I will not go into the detail now. We have been working on various device structures like the graphene, and then we put a layer of boron nitride in between the graphene layer and the chalcogen layer in order to, we wanted to initially to see if we can get energy transfer, but that didn't work out well. But we have been working on nanowires, on graphene heterohybrids, and so on and so forth. And we have been able to, because by doing this, we have been able to get responsivity, very large responsivity in the infrared regime for technological purposes. Okay. Right. So that's more or less what I wanted to talk about this charge transfer. But let us talk a little bit about how do we change the energy? How do we tune the energy transfer in these kind of heterostructures? Okay. So, for example, for this, we wanted to have a model system, and a twisted bilayer graphene turned out to be a very interesting system in which two layers of graphene are kept within the van der Waals distance, and we wanted to know how heat or photons are getting transferred from one layer to the other. Okay, so just to give you a very brief introduction to what a twisted bilayer graphene is, you know graphene per se, and which is essentially like this, and a twisted bilayer graphene is essentially just another layer which is sitting on top. Okay, so now we can twist it. We can just rotate it one respectively to each other, and this is something which now students here can do very accurately, and this has led to a very interesting set of activities. I'm going to talk just about one. And you can change this angle at your own will. And you can see that as you change the angle, you create these larger scale structures, which are called moire lattice. Okay, so whose lattice parameter is much larger than the unit cell of individual graphene layers. So it's like a new super lattice that you can form by applying two layers of graphene. Okay, and you can change its lattice constant by changing the angle between two layers. Okay, and the very interesting idea here is that when the angle between two layers is large, what happens is it's 9.43 degrees, for example. You can see the low energy structure is almost conical, like what happens in the case of single layer graphene, which means that the two layers are essentially decoupled. However, as the angle goes down like this, I can see that angle is about 3 degrees. This Fermi velocity starts decreasing. You can see the slope is decreasing further, and eventually when it comes to about 1.4 degrees, there's a magic angle that is formed, and you create what you call flat electronic bands, and that led to strong correlation physics, and so on and so forth. Okay, so this has been one of the latest kid in the block in terms of craze and activity in terms of new phenomena, and that has been shown. And however, here essentially there is supposed to be no coupling between the two layers. Okay, and these has at around 1.1 degrees. The superconductivity, because of strong correlation, has been claimed. Although it is still a very open question, because whether really the superconductivity is a strong correlation effect or not, or at least how much role the correlation plays in the observation of superconductivity, something which is a matter of completely open debate, even after 2 years of more than 2 years of publication. Okay, but it turns out that electronic hybridization is not the only hybridization. Even the lattices hybridize between the two upper and lower. So this is one of the most important effect of this hybridization of the two layers is what is called the Z optical phonon, ZO phonons, which is essentially the low energy optical phonons. You can see this essentially is because of the two layers are vibrating in exactly pi phase, and these are the two. This is the cartoon here, and that leads to this. Depending on the Q, gives us a new phonon band called the ZO phonons, and their energy is in the order of 100 centimeter inverse or about 100 K. And so forth. Okay, so there are shear modes as well, but we will concentrate at this point on the ZO phonon. Okay, so both electrons and the holes and the lattice can hybridize in these heterostructures. Right. So this is what the experiment was at some. This is about 3 years old. So we wanted to pass current in the upper layer. So you create a. I'm just drawing. I don't know whether it's possible. So we have this upper layer, and we pass current in this, which is called a heating current, and we measure the voltage between the upper layer and lower layer. Okay. So it's essentially a thermoelectric potential. Okay. So using a high heating, you heat up one layer with respect to the other and measure the voltage across the two layers, across the Bangalore gap. So important what you understand here is that we really are asking the question about what is the thermoelectric or figure of merit or thermoelectric property of the smallest scale of formation of a solid. Van der Waals distance is really one of the shortest atomic scale that we can think of. So that's the question. That's the engineering of charge and heat flow that we can do now. Before we go understand that, I have about 5-6 minutes, Pankaj.
Than that.
More than that, you have 15 minutes more.
Nearly 20 minutes.
Okay. I will not take that much, but anyway, we will have questions. Okay, good. So let us talk about a little bit of thermoelectricity. Okay, so we see that when you have a thermoelectric material, if you apply a potential across it, apply a temperature difference between two layers, between two ends, you get a voltage, right? And that's what you call a thermoelectric voltage, or a Seebeck voltage. Opposite, if you apply a voltage and that leads to temperature difference, you have a potential. Okay. So normally the voltage that is obtained is determined by the impurity scattering and phonon scattering. Okay, impurity scattering usually gives you, because while the electron is going from the high temperature end to the low temperature end, it keeps on scattering with impurities and photons and phonons. Okay, so this leads to two types of thermopower. One is called the diffusion thermopower, SD, and other is the phonon drag, SG. Okay, so the phonon drag is essentially given by the occupation number of phonons, obviously, because how many phonons you have will determine what will be the voltage difference that you can create between two ends. Okay, and then the diffusion thermopower is, of course, because of the static impurities in the system. If you take a look at gallium arsenide kind of system or any kind of other semiconductors, then the phonon drag essentially dominates the thermoelectric power to most temperature range down to millikelvin. Okay, so the question is, how do you analyze thermopower? And the semiclassical Boltzmann transport is one of the most celebrated ways. And if you look at through your Ashcroft-Mermin or any of the standard solid-state physics book, you will see that Boltzmann transport gives us electrical potential difference and thermoelectric potential difference in the same relaxation time formalism, in which you have J, the net current, is given by the electric field and as well as the temperature gradient. Okay, and they are related to each other through the scattering time cube, energy equivalence of scattering time. And this is what you call the Mott formula, in which the thermoelectric parameter or the Seebeck coefficient is given by the ratio of the potential and the temperature differences, and which, if you look at the final result of it, is a derivative of conductance with respect to energy. Okay, and this essentially is this number. Excuse me. Now, what happens is this number delta G d log G d log E can be decomposed into two parts, which is 1 over G dG dN, which is determined from experiments, because we are always measuring conductance as a function of gate voltage, and gate voltage essentially changes the density. So 1 over G dG dN is essentially an experimentally determined number, and the dG dN dE is essentially a number which is given by the density of states, okay, the number of states per unit energy at the Fermi energy. So what happens is these two combination, if you know from your system, then you should be able to predict what is the Mott or the thermoelectric figure of merit of a system. Okay. So this is an example. This is data of Aditya Jayaraman, who is about to finish his PhD, and hopefully this paper is going to come out soon. So this is a typical graphene. I mean, this was taken in a bilayer graphene, but there is nothing special about bilayer graphene here. In this case, you can see that this is R versus Vg, or the density of bilayer graphene. And this is the corresponding figure of merit, this is the corresponding thermal voltage measured by applying a temperature difference across the two layers, okay, across the graphene layer. So what happens is you can see the bilayer graphene being a standard parabolic band structure, the density of states is constant, and 1 over G dG dN comes from the experiment, and we can compute this number, and then you can see that the experimental value of the thermal voltage exactly matches what you get from computation. So that means bilayer graphene obeys Mott formula very nicely. It's a semi-classical system per se. However, if you want to measure it across the two layers, I just took that example to show you that how Seebeck coefficient is analyzed in this context. But now the question is that we will put one graphene on top of each other and measure the potential across the two. So you start with silicon and silicon oxide. You put a boron nitride layer because this is a nice environment for the graphene. Then you put a layer of graphene. Then you put another layer of graphene across so that you can put electrical contacts wherever you want. And then put another layer of boron nitride to cover it, make a nice and clear high mobility region. And then you put your gates and electrical contacts. Okay. What you do is that you vary this potential on this gate here on the top, it's called a top gate, to change the electron density in the overlap region so that you can measure the thermoelectric as well as electrical properties only where the two graphene layers overlap. Okay? So that's the reason. That is of our interest. This is how our device looks like. As I always say that the cartoon looks much better than the actual device, and it is far more difficult to make an actual device than the cartoon. I make the cartoon, students make the device. Okay. So let me tell you how the electrical properties look. As you can see now, we are talking about cross-plane electrical properties, in which this is one layer and this is the second layer. But then I have passed current from the upper layer to lower layer and measure the voltage between the upper layer and lower layer. So it's an electrical property. If this is the two layers, this voltage is essentially dropped between two layers. Okay, so that is giving us this R cross plane. So I know the current, I know the resistance, and as you can see that as you apply the potential, this goes down on both sides, because this region, overlap region, is getting doped by the top gate. Now, if I want to measure the thermoelectric potential, in which now what we are doing is that I have got an upper layer and lower layer. In this case, I had current as well here, but here I have only one current in this direction, which is the heating current, and now I am measuring this voltage, which is called thermal voltage. Okay, so this voltage is plotted. You can see over here, and as you increase the heating current, this voltage increases continuously. This is from 1 micron to 3.8 micron. And if I scale the heating voltage, you can see the over here we had heating current. I scale this voltage by the square of the heating current because it's thermal voltage. I get all curves exactly collapsing on each other, and that tells us that this is nothing but because of thermal or heating oriented origin. So I'm transferring heat from upper layer to the lower layer. Okay. So we can measure the temperatures of the two layers independently, and you can see the delta T between two layers can be, and this is something which is staggering. If you see the inset here, at a heating current of 5 to 10 microampere in the upper layer, you can actually create a temperature difference of 30 to 40 Kelvin, and this is large, 30 to 30 Kelvin at least, between two layers which are separated by 0.5 nanometer or less, which is, if you think about the scale, it's staggering. But what is interesting about this is that if I look at this thermal Seebeck coefficient, now by dividing the delta T by the thermal voltage by delta T, I have got the Seebeck coefficient. You see, Seebeck coefficient at different gate voltages is not a linearly dependent quantity as you would expect from the Mott relation. A Mott relation, Seebeck coefficient is proportional to temperature, but in this case, it is not so. The temperature at every gate voltage for given density, the Seebeck coefficient essentially increases fast and then saturates. It turns out that we can understand it in a very elegant manner, and that is simply by looking at the phonon number in the two layers. For example, when you have the upper layer, it is this upper layer, it is a hot layer, and the number of phonons are larger in comparison to the lower layer, which is colder. Okay. As a result, the electron essentially gets scattered more out of this layer and goes into the lower layer because there are more phonons to kick those electrons out. Okay. As a result, the thermoelectric voltage that you generate, delta V over delta T, essentially turns out to be the derivative of the phonon occupation number with respect to temperature. Okay. And it turns out that if I use the Bose-Einstein occupation for phonons, you can fit the Seebeck voltage as a function of temperature exactly. Okay. In addition, it actually gives you the phonon frequency, which is responsible for kicking these electrons out from one layer to the other. And this turns out to be exactly the electrons. So you can see that at the center of the zone, which is at 0 kF, the energy of the phonons experimentally we get about 100 Kelvin, which is nothing but the energy of the phonons because of the ZO phonons, which is becoming because of the hybridization of the out of plane vibration between the two layers. Okay, so that was very interesting, and what we found that this is something which is not true. I mean, this saturation of thermoelectric voltage as a function of temperature is essentially it's not true. It's the only way that the theta, the angle between two layers. Now I'm coming to what happens as a function of angle of the between two layers. Yeah.
So basically, if you go back to one slide before, then doesn't it defeat your purpose? The one more.
Yep.
Doesn't it defeat the purpose when you have the upper layer? You have all these phonons coming to the lower layer and heating it up. So you want to continuously cool a device. So you have a device connected to the lower layer. And you have a device connected to the upper layer, and your idea is to take the heat away from from one layer and keep the heat in the other layer, so that the lower layer becomes gets cooler and cooler.
Right.
But because of these phonons, it is this jeopardizing your device.
Absolutely, Saurabh, you are absolutely spot on here. Because what happens is because of the hybridization of phonons, you are essentially leaking the heat out, and there is a thermal conductivity between upper layer and lower layer. Okay, we originally started thinking that we can actually have a complete thermal insulation between the two, but because of the hybridization of the two phonons, you are no longer able to maintain the temperature difference. Let me put it this way. Because if you want to have a heat engine, then you want to maintain a temperature difference, and this will be a high efficiency temperature heat engine. High ZT factors is what you call. But because of this phonons, which is coupling between the upper layer and lower layer, you can no longer keep that temperature difference.
Yeah,
you're absolutely spot on there. And you're actually telling what we are now doing. What we are doing there is that we are now inserting foreign layers in between the two graphene layers, which can jeopardize the lattice hybridization without jeopardizing the electrical coupling too much. See, the advantage here is that you can couple the two layers structurally, independent of the way you can couple them electronically. Okay, and that's very interesting, and that's what I call. I'm going to end with that actually. That's what we call a complete, bottom-up emulation of a thermoelectric material. Okay?
But is it possible that you completely detune the phonons in the two layers by making one of them a little rigid and the other not so much, so that when it scatters, it doesn't really come to the the bottom layer?
Absolutely, that's a great idea. Answer is yes, you can. And people, although not in this context, but people have been doing this to stagger the lattices of graphene by applying a boron nitride 2D potential, for example. Say if you put this thing on boron nitride, then the boron nitride is nearly lattice constant of graphene, but not fully equal. There's about 0.2% of difference. So it staggers the potential of one of the layers, and that can detune the two phonons quite possibly. So answer is yes, and there's a lot of scope of imagination, and how to improve the thermal decoupling between the two layers and it can actually lead to a very strongly application oriented as well as fundamental. Heat flow through these are very important topic now. Okay, so you're absolutely right. So in both the ideas. So anyway, so we have found that that if you don't do anything, then it's the hybridization of the two phonons, two layers in terms of crystal lattice vibration, essentially dominates the electron transfer from one layer to the other. So, or we can say alternatively, what we really are seeing is a Coulomb drag at the atomic scale. So Coulomb drag also does the same thing. We have phonons which are a number gradient, and that leads to potential difference. What we are looking at here is really phonon drag at 0.3 nanometer distance. Okay, but that's not the entire story, and this is something which hopefully will come up very soon. So we see these phonons are dominating the show only when the angle between the two layers are more than 5 degrees or around so. Okay, whereas if the angle between the two layers is small compared to is smaller than 5 degrees, then we recover what you have as Mott law, in which the thermoelectric power is directly proportional to temperature. Okay, and we believe we understand this now, and I'll just end this with this understanding is you see, this is if you take two layers of graphene, then this was the old theory of Mitchell and McDonald, and essentially it models the two graphene layers as a RC time constant, and in which you have the tunneling probability, calculate the tunneling probability of electron from one layer to the other as a function of the two layers, the misorientation of the two layers. It's just plain and simple calculating the hopping matrix element between two layers. Okay, and then you get this pattern. Now, if you look at the kind of range that we have in terms of, so the phonon frequency, this is log to the base 10, the phonon frequency is somewhere here, okay? And the angle, corresponding angle is about 4 to 5 or 5 to 6 degrees, okay? At which the phonon frequency becomes, for larger angle, the phonon frequency is larger than the electron tunneling or hopping probability from hopping rate from one layer to the other. Whereas when the angle between the two layers is small compared to this 5 or 6 degrees, phonon frequency is smaller and the hopping matrix element is larger between the two layers. So that kind of gives us the clue what is happening there. It turns out that when the two layers are closely aligned below 5 degrees, then you have the electron tunneling is essentially dominating, and phonon frequency is a slow process in comparison, and it is not really affecting the thermoelectric power at all. It is obeying the Mott relation because we are in the diffusion, or the Landau-Boettcher regime, in which you calculate the transfer from one layer to the other.
I know one more interruption, but it looks a little counterintuitive, because your smaller frequency would give rise to a Dirac kind of physics, which means the two layers are coupled. So that's a relativistic dispersion. And that S equal to S proportional to T is a Sommerfeld type of relation, or Drude relation, or whatever you want to call it.
Absolutely.
So how is that? Because that's on a K-square kind of dispersion.
Correct.
So how does this?
Yeah. So again, let me tell Saurabh, you are asking questions which are happening now, but I'll try to give you the answer. See, it turns out that below 5 to 6 degrees here, the two layers are starting to talk to each other by hopping up electrons from one layer to the other. But the hybridization is still not completely leading to reconstruction of the Dirac bands. Okay. It turns out that a significant amount of reconstruction or the modification happens when you go below around in a small regime, particularly the other effect starts coming in, which is around 1.5 to 1.5 degrees or something of that sort, around that region. Above that angle, so below, say for example, 1.5 to 2 degree onwards to about 5 to 6 degrees, yes, the electron hopping is the dominant phenomenon, but it is still two single layer graphene Dirac bands that are relatively decoupled from each other. Whereas in the case of, we understand what happens at larger angle. At a larger angle, essentially, it's a phonon frequency, which is the faster process. And that kicks out the electrons before the electrons can hop itself from one layer to the other. And that is why we see the saturation or the phonon drag kind of effect at larger angle devices.
Yeah, okay. I get it now. Yeah. So it's a competition.
Okay, so that's essentially the discussion I wanted to have. I think we're actually spot on time. So what I wanted to give you today in this colloquium is that van der Waals heterostructuring can essentially lead to a very different material architecture and a very different imagination-based method of engineering material or device functionalities in a bottom-up manner, in which you design what you want to do, and then you put the materials based on your physics understanding of it. If you want to control phonons, whether you want to control electron hopping from one layer to the other. So it's really, you are using your physics understanding to make a functionality of a device. I have given two demonstrations of this, of the controlling the light-induced charge flow, which leads to the world's most sensitive detector of light, which is naturally a very interesting, what we have done there is that we use the absorption capacity of a molybdenum disulfide or a transition metal dichalcogenide layer and the electrical transport capability of graphene. So essentially, light is being absorbed in the lower layer, which is the semiconductor layer, and the electrical transport is happening in the upper layer, which is high mobility graphene, and hence you combine the best of both worlds to get a photodetection of extremely high quality and efficiency. And the heat flow by the layer is something which shows that we are in a position to engineer the heat transport by either detuning the phonons or by changing the layer orientation or some other route. And we, in principle, can not only go to very highly interesting device capability, high ZT factor, high thermoelectric figure of merit, but we can also look at new effects, which I did not talk about at all, which hopefully will come in the next colloquium I give to IIT Guwahati. All right, thank you very much for your attention.
So thank you, Arindam, for such a illuminating talk, and it was very interesting. So now we have time for questions.
Can I ask a question?
Sure. Do you want me to stop sharing, or I can continue sharing?
No, you keep it sharing. You keep it sharing.
Yeah. Please.
I have a question about some slide, but my question is rather silly, so please forgive me if it sounds very primitive. My question is the following: that when you compare your experimental results with theoretical modeling, do those theories take into account the fact that screening is very poor in graphene, and an independent particle picture, I don't know to what extent people still rely on that. I'm not following the literature very closely. So to what extent do people still rely on this tight binding model without interactions in graphene? And because from my limited understanding, screening is very poor, and it may not be a wise way to do that.
I mean, before Arindam answers, the kinetic energy is extremely large in for the 2s electron, the hybridized, one of the two sp2 hybridized electron. It's an extremely high kinetic energy, so it should be good. What do you say?
Yeah. So first of all, this question is certainly not irrelevant. So this is a very important question of screening. And in fact, our referee of these the thermoelectric data has actually raised several questions and objections, because often our analysis of the experimental data did not consider screening explicitly. For example, if you are looking at the lower layer of graphene, and we are applying a gate voltage from the top to populate the two layers and looking at its thermal or electronic properties, one layer will screen the top gate voltage to determine what is happening in the other layer. Now, it turns out that there seems to be quite a bit of, I wouldn't say disagreement, but openness in this whole issue. The screening of the single layer graphene, in spite of the fact that the kinetic energy within the layer is extremely large, because it's so thin, and if you calculate, I think the screening is not so strong. So it doesn't screen too much. And we have been trying to, hopefully we have been able to now convince the referee that when you apply a gate voltage, there has been earlier work in which the net electron density that is there in the two layers are almost equally distributed, which means that graphene screening is very, very small. Most of our experimental data actually seem to agree with very low screening of graphene. But it's a question which probably a specific computation can answer better.
Okay, yeah, Professor Giri, go ahead.
Okay. This is P.K. Giri. I am an experimentalist.
Yes.
We have met sometime.
We have met.
A lot of topics you have covered. I am a bit interested on this twistronics, which has been done mostly on graphene.
Yeah.
What about the other, particularly TMD, if you have a combination or heterostructure?
Yes.
How do you really control, and what is the easiest way to measure this twist angle?
Okay.
Without microscopy.
Okay. So you are asking about the TMD twisted TMDs.
Yeah.
Okay. I'm actually very sorry, because we just published a paper, and unfortunately the student who did it is not well. I wanted to have a slide on that, but that didn't work out. So we have this TMD of molybdenum disulfide, and now several new members of the group are working full time on the twisted TMDs and looking at both their structure as well as optical properties. So let me, in a very quick point here, first of all, in order to know the angle, it turns out that in case of MOS2, there is a very easy way of doing it. That is, you look at the angles which are 60 degrees corners, and those edges turn out to be zigzag edges. And then you take two of those zigzag edges and you put them together. And then you can, and there is a continuum mechanical calculations as well as experiment, which shows that when you get exact 60 degrees in a twisted in a molybdenum disulfide layer, it turns out that those edges are zigzag edges. Okay, so you can actually not only lay angles with lay two layers at 60 degrees at 0 degrees, but you can actually do from 0 degree to 60 degrees, because unlike graphene, the 0 degree and 60 degrees for the twisted TMDs are two physically separate entities, because the positioning of the molybdenum and the sulfur changes when it is 0 and when it is 60. And that makes a huge difference in its physical properties. So we have found that now, and we have done some Raman spectroscopy on that. And we have found out that the electronic coupling, electron-photon coupling between two layers changes from large value at 0 and 60 to a small value in the 30 region, okay, which has been computed as well. I'm really sorry I could not do that, but the determination, I hope I gave you an idea of how to determine the angle. So essentially, if you can see my screen.
Is there any calibration? Like, for example, from Raman, can I say that there is a twist and that is the standard technique for determining number of layers? So
in the case of, yes, you can, but for that you need to have these shear modes. So if you know the shear modes of this twisted bilayer of MOS2s, you can tell the angle. Okay. But if you don't want to use the angle, then you can if you don't have a Raman spectrometer which goes to say below 50 centimeter inverse, you cannot measure the shear modes.
Low frequency.
Okay, so shear modes give you the angle.
Okay, thank you.
Okay, so some questions from a student.
Yeah, please.
Arindam, I have some questions. Pankaj, can I go ahead?
Yeah.
Okay. So Arindam, first of all, very nice talk, extremely well delivered. And I really like your last slide. It is very similar to, another stalwart in the field, Zahid Hassan. He talks about similar things. He can make anything with these 2D materials. All right. The question is that what about, what's your take on the other kind of van der Waals materials such as Bi2Se3, SB2T3 and all that? Why don't you consider them as well for applications? I mean, I have some very minuscule experience with them. They're nice weakly coupled van der Waals layer, and you can put something inside the layer, which is precisely when you mentioned that we are trying to put something between the layers and all that. So what is your take on that? Yeah.
Okay, before I forget, let me answer this specifically.
Okay.
So first of all, sort of the Bi2Se3 or the standard topological insulators are interesting in their own right, not just for putting inside others. And now we have done a lot of work with in collaboration with Nitin Samarth at Penn State, along with Saurav Islam and Shavanti Bhattacharya. So they are the PhD students on that, measuring the electrical transport in that system. Now the question is, okay, so you can look at completely topological insulator physics over there, and you can look at quantum spin Hall effect and so all sorts of very interesting phenomena. As far as the van der Waals engineering is concerned, in which you try to couple these materials on top of each other, it's less of a popular material simply because the quality of the material is something which is, when you have to transferring the material means you have to get single crystals of them and then you transfer them on graphene for whatever purpose. Again, you have to define what the purpose is. We have started something of that sort, looking at the optical property of this bismuth selenide graphene hybrids, trying to see if the low band gap semiconductors can actually operate through a surface state which is metallic. So there are off and on work on that, but I don't think there has been a significant amount of effort in that, primarily because I think the advantages are not particularly clear at this stage. So that's, I would say, the reason. But we have worked on the individual topological insulators quite a bit.
So one question from my side, one naive question, can I ask?
Yeah.
Please.
Yeah. So generally you showed this thing that graphene, when it is twisted at magic angle, then you can get a very high conductivity due to the fast electrons. So can we have such kind of things in other 2D material, and can that be the way for the high TC superconductivity at room temperature?
Okay, let me understand the question first. I mean, you said that we, when we encapsulate graphene by boron nitride, because of the lattice matching, you get very large mobility. That's the way to increase the electrical mobility of these samples. Now, there has been work on encapsulating molybdenum disulfide, for example, to improve its quality. And there has been some success in that. Although, as I said in answering Saurabh's question, is that one of the challenges in other systems is the quality of the material. Whether it is topological insulators like bismuth selenide telluride or even molybdenum disulfide. So the intrinsic crystal quality is not great, unlike graphene, and hence even by encapsulating, I don't think the increase is massive. Okay, so that's one of the problems. Now, I cannot see that whether this can lead to room temperature or high temperature superconductivity. The reason behind superconductivity in these samples is primarily because of electronic hybridization that you do by control. It has nothing to do with the quality of the material. I mean, quality of the material is the base requirement, but then you hybridize to create a new band structure. Okay? So these are two different problems. Just by improving the quality, you will not get the other, superconductivity or any other functionality or magnetism, for example. So those things are not going to come unless you do some band hybridization.
Okay. So any other question? Uday?
May I have a question? So, this is
Uday
from Department of Physics. So I have some question regarding whenever you are transferring any of your 2D materials like graphene on the SiO2 substrate for device fabrication. So there is always chance of trap charges in between this graphene and the surface charges, and it leads to some charge puddle. So my question is whether this formation of heterostructure can actually minimize the effect of these trap charges. I mean, due to the screening effect.
Yes, so that's a very good question. In fact, these days, if you ask the students, they use a graphite gate instead of silicon oxide. So what happens is on silicon oxide, you put a graphite, which is like a really metallic system. And normally, most of these traps come from silicon oxide, as you correctly said. Excuse me. Although, that said, we have recently published a paper, Saloni and others did the very nice, interesting work, in which we showed that our residual scattering is coming from the lattice defects in boron nitride, which is really surprising. Boron nitride is supposed to be, and we get boron nitride from Japan, one of the best quality boron nitride that is available on Earth. And even then, the scattering now is no longer by, or mostly suppressed from those in the silicon oxide, but the defects in boron nitride actually can end up scattering. Okay, so we have to find ways in which we can, if we can.
So it's kind of remote interfacial scattering, you mean?
The defects in boron nitride, no. That is defect because the boron nitride encapsulation is a bulk in the sense about 10-15 nanometer thick boron nitride. So there are bulk defects in that. So those defects essentially start scattering electrons, which is in graphene. Yeah.
Thank you. Thank you.
Arindam, can you go to that slide where you have all these gate, yellow color device on which you put a gate and all that? This one. Yeah. So there is, there are reports in literature that you can tune the spin orbit coupling using the gate voltage because you can make a gradient. And so there will be a Rajba kind of term that will, come because, so this. So that would eventually give rise to spintronic applications. Is there any thing that in your mind in that direction?
Yeah, that's a great question, Sonu. So let me put it, say the way people have been trying, actually to some extent, maybe this will answer your business line question also. So it turns out that spintronic applications, people are trying with these structures because graphene itself is not, it's very light atom, no intrinsic spin-orbit interaction, hardly any at all. So people are trying using proximity-induced effect. So, and there have been nature physics papers just in the last year. And what you do is that you take this tungsten disulfide or tungsten diselenide, which is like TMDCs, but those are strongly spin-orbit coupled material. There's a semiconductors, but those you put on below graphene because they don't contribute to electrical charge transport. But they essentially make the graphene electrons, this induces some spin orbit interaction to graphene layers. And with that, people have found out some topological insulator behavior, some non-locality in the current flow, which is and the spin effects. So those are the directions people are thinking at this point. As far as we are concerned, I am not doing that in my group, but there are other people like Avik here who is probably doing some work in that direction.
So spin polarized current or spin torque, these are things that you can measure in your lab?
Yeah. So as far as the basic measurement facilities or measurement capabilities are concerned, there's absolutely all here. Even devices making are all simple. It's just that whether you want to, that is the research direction. As a group, we have not looked at the spin torque effect or essentially spin diffusion in a spintronic sense in graphene heterostructures, but it is available now. And it can be easily done.
Okay. Yeah, great.
Yeah. So any other question? Student, ask the question. You can see that how beautifully they have achieved many things in the laboratory experiment, and that can become the next generation technology also. Please ask the question. Or if not, you can contact to a speaker also any point of time.
Yes, please write to me, and if you have a question, I will be very happy to get back to you.
Okay, so if there is no further question, so we'll have to end some good thing here. And with this, we are really grateful to Arindam for delivering such a beautiful talk and taking us a great tour of all the development that is taking place in his lab. And it was really wonderful to see the things happening at the atomic scale, and that they are able to tune the things in such a fine way and can get the beautiful phenomena. And we hope that in future we'll have many opportunity to listen more interesting thing from his lab, and at some point of time we would also like him to...
Okay, there's one question just to answer that. What is the Chern number in this case? In case of bilateral, the Chern number is 2. Whereas in the case of BHZ model, which is the Chern number is 1. So there's a difference.
Some student asked this question because Saurabh also introduced one course in PhD, advanced condensed matter physics, and in that he specifically put that topic, and some PhD course he also going on. So many students basically are more interested to know about those things. So,
but this I don't sort of agree too much. I mean, you can have a it's not like a Chern gap. That's the only thing. It's not like a Holden gap. There's no time reversal.
I totally agree with you. It's not.
Okay.
So, which is why it's not really called a topological insulator, but it's called a marginal topological insulator. You can easily break the protection.
Yeah.
But you can still get edge current when you gap it out.
Yeah. There are. So that's why you call it marginal. That's a very nice name, actually. Yeah.
So Arindam, thanks a lot. Okay, and so it was unique talk also, because so far we had talked with the specific topics, and this was a talk lying between the science and engineering, and so it added great variety in our colloquium. So thanks for agreeing and giving the colloquium talk.
Thanks, Bhagat. Thanks, Saurabh. We'll catch up again.
Okay. Bye. Bye.
Take care.